Okay, thank you very much. Thank you for the invitation and to be here. And it's a good place to start this talk since Patrick and Mike have sort of set the scene for what I'm going to talk about. The original title was just sort of this bit here and D double prime, but we got inspired to add a bit of other stuff, and I hope you're not going to rush off to lunch as soon as you can, because I might not finish in time. But anyway, so defects and diffusion obviously are important for various reasons, but one of the points that Patrick made as well was that it can have a central role in controlling rheology. In particular, it was pointed out that there are these diffusion mechanisms such as basically diffusion creep and also climb, which is a diffusion-controlled process. So the story about which is ongoing at the moment. And so we've been, whoa, fantastic colours. They're not at all the colours on my screen. Brilliant. Anyway, okay, so this has nothing to do with the talk, really, except that it's leading me just to sort of tell you a little bit about the mechanisms. Okay, so over here, this is actually a simulation, a molecular dynamics simulation, an ab initio molecular dynamics simulations. Okay, well, the forces are calculated from first principles, that is, we're trying to solve with some approximations the Schrödinger's equation for this big system. Okay, over here is melt and here is solid, and in time this simulation will actually melt, and it's part of a study I did some time ago, which never quite got around to publishing, about trying to calculate the melting temperature of perovskite. But it tells you a couple of things. One is if you follow atoms in here in the melt part, they diffuse, they just move through the melt, and just by following them and calculating their root mean displacement, you can calculate the diffusion coefficient directly. In the solid part, which is now little by little gradually disappearing, and I think it's probably all melt now, there is no diffusion, okay, because in the timescale of these simulations, jumps are so infrequent that you can't calculate them in this sort of a direct manner, and we have to take a slightly more fiddly approach, I suppose. The one exception that I know of is actually helium diffusion in perovskite, and this is some work that I'm doing at the moment and it's ongoing. This is a simulation cell of, actually it doesn't matter, but of perovskite. And the little white balls here are the positions of a helium atom at every 10 time steps through the simulation. Okay, so and I've just frozen the perovskite structure just to make it clear for you. So in this case, actually, helium diffuses all the way through the structure very nicely, and you could probably try to make an estimate of the diffusion coefficient of helium from this way. But for most things, that's not possible for most solids. Okay, so we have to take a sort of a slightly more convoluted step. It's a very interesting set of colours we've got going on here. Ah, okay. Aha. I want to go back now. No, that's what they should have looked like. Okay. Right. Okay, so now we've got the colours. Okay, good. So this is basically how we do it. Okay, so diffusion in general, with the exception of helium, which is going interstitially, almost always goes via some sort of vacancy mechanism. There are interstitial mechanisms as well, but we're only really considering the vacancy mechanisms because that's what we think generally happens. So you might have a vacancy over here. This is the magnesium, and it's got to jump from the initial start place over some sort of saddle point to the final point. And of course, what you want to do is calculate the energy of that jump, and that gives you the migration enthalpy here, which goes into the self-diffusion coefficient. You also need to know something about the attempt frequency and the entropy of this process. And again, you can calculate these within certain approximations quite well, very well, in fact. And rather than try to persuade you that they're brilliant, what I'm going to do is just sort of show you the results in comparison with some of the experiments. And you can hopefully see that they're pretty good, certainly good enough for what we want to do. Okay, so there are these ways of doing it. We calculate these parts just from the frequencies, the vibrational frequencies at the initial point and at the saddle point. And it's reasonably, all that's done via first principles. We came into this initially wanting to look at silicon diffusion. That's because, of course, back there was a discrepancy. Wright and Price did some theoretical calculations showing that silicon diffusion of migration enthalpy was about 9.4, really huge number, meaning silicon would never ever diffuse pretty much. The experiments came along and said it was about actually much lower at 3.6, and then Karki did some more theory showing it was about 9 eV, and then the experimentalists came along and guessed, oh no, it's 3.7. So we thought we'd have a look at that. And this is roughly what we're trying to calculate. You can see basically in here is one missing silicon. There's a silicon here that it diffuses through, and this is the energy that we want to calculate, the highest energy path that it goes through. And as you can see, it's actually quite a complicated process. These oxygens sort of move around a lot and come out and collect it almost and catapult the silicon into this site. And we can calculate the energies at all that point along, and then we can come up with some sort of an energy or an enthalpy for this process. And we came up with a number of about 5 or so, which was a lot better than 9 eV, but still not really good enough, although we did actually publish it thinking that was a lot better. It turns out that for fun, it's actually a lot more interesting process than we thought at first. In fact, silicon doesn't really diffuse via a direct mechanism at all. In fact, this is one of the mechanisms that we came up with, and it's important to understand these mechanisms because there's no point calculating the energy for an incorrect mechanism because that doesn't tell you anything. You want the easiest path. Okay? In fact, this mechanism I now think is not quite right either, but it doesn't really matter for the moment. Okay, so it goes a bit like this. Okay, here we are. Up here is a nice silicon vacancy. Okay, you can see the octahedra here. This is what and there's 2 magnesiums. The little black things are the oxygens. Okay, and what happens? The first thing that we see happen actually is that rather than the silicon making its direct move from here to there, as sort of like this. Okay, what happens is you have this 6-jump cycle, which is quite interesting. The first thing that happens actually is the magnesium jumps into the silicon site, and you have something like this, where you now have a magnesium vacancy, and you have magnesium in the silicon site. The next thing that happens actually is this other magnesium here. The silicon jumps out of its octahedra into the interstitial site, giving this sort of a thing. Then this other magnesium that's over here, that started over here, jumps into the empty silicon site, and you have this rather bizarre structure here where you've actually got 2 magnesium octahedra and a silicon in the magnesium site and a vacancy. And then the whole thing starts to unwind, and you get to this place here where the silicon has essentially made one jump, or the vacancy has made one jump. Okay? And it turns out if you add up all of those little bits of energy, you actually come to a remarkable agreement about exactly what the experiments say. Now, there have been some slightly newer experiments which have suggested it's about 3.4, but the error is within that. So this was our best guess for that. So how did that? So that gives you the migration enthalpy, okay, which is really the slope of these curves. If we want the real diffusion coefficient, we also need to know something about the vacancy concentrations, and that's very problematic, and it still is a problem, although again I think we're making some progress on that, although I'm not going to talk about it today too much. Up here is oxygen diffusion. All of the points up here are sort of various experimental data, and these lines here are our results. I'm not going to worry about how we got the thickness of these lines at the moment. And here is what we would predict oxygen diffusion to look like with about 0.1% vacancies. The 0.1% vacancies is quite good because it actually agrees well with the amount of doping that was done in these experiments to get you those vacancies. So that agrees nicely with that. I'll skip MgO for a minute because I've got another slide on that. And here again, here is magnesium and silicon diffusion, and here are the experiments, and here are our results. And again, they agree pretty well. Okay, you might say, well, there's a sort of an order of magnitude difference or so, but actually, there's many orders of magnitude difference between the different species, and so actually, that's pretty good, I think. Okay, MgO, we can say more or less the same thing, that we're able to pretty much predict most of the experiments when we use reasonable, experimentally constrained vacancy concentrations. Okay, so those are just the sort of the pure MgSiO3 and MgO, and iron was brought up. What about iron? Now, iron has been argued for a long time. Well, it's been suggested, of course, that it undergoes this sort of spin transition. Okay, where you have your Eg and T2G levels here occupied in such a way, so you've got 5 up and 1 down, giving you a net spin of 2. Okay, and as you increase pressure, this energy increases such that it's more favorable in the end to actually pair the electrons in these orbitals. Okay, so this is the spin collapse. This is for an octahedral type arrangement. Okay, and of course people have argued that this has a big effect on just about everything. Okay, densities, seismic velocities, electrical conductivity, diffusion, rheology. I don't know. There are other things, I'm sure. Thermal conductivity. Okay, so we thought, well, let's have a little look at that. Oh, in fact, here we go. Well, okay, so in ferropericlase, it definitely has some sort of effect. It's pretty clear that Fe2+ undergoes this sort of spin transition. In perovskite, it's not so clear yet what's happening. There's clearly some sort of a spin transition. It's probably ferric ion. The ferrous ion probably stays low spin, stays high spin. So I'll leave that for the side, but we'll just worry about ferropericlase. And it's clear, for instance, that the density and the adiabatic bulk modulus here are affected by the spin transition. Here are a bunch of calculations from Renato Wentzkowicz and so on, and here are some data of theirs, not theirs, some other data showing this change. Much smaller effect on the velocity, and there's an effect on the bulk sound velocity as well. And as you increase temperature, this gets smoothed out a lot. Okay. What they argued actually in this paper, 2009, was actually that this also could affect the viscosity of the lower mantle. Okay. And so we thought we'd have a look at that, and they would, on this sort of complicated pitch, I don't want to go into it, but they just sort of suggested that this sort of dip that you sometimes see in the data or in various inversions for the viscosity may actually be due to this spin collapse. Okay. Well, I mean, turns out life is never simple. So what we thought we should just calculate was, okay, so here's a high spin ion sitting in its initial state, and it's got to jump over to some other state here, and we'll just calculate the energy as it goes across, right? So that's straightforward. We can do that, and we thought then we'd do a low spin calculation. Okay, we'll constrain the simulation to be a low spin simulation, and we'd just measure this other barrier, and then we'd see, well, you know, which one's bigger and which one's smaller. Does diffusion, is it faster or slower in high spin or low spin? You might think the high spin is the low spin is a smaller ion, maybe it can pop through the holes better, okay? Well, it turns out that, and this is interesting, because if you're going to start doing ion in your dislocation, you're going to have to worry about all of this too. Turns out that actually during the motion, the low spin ion actually reverts back to a high spin ion, okay? So for this energy, this is fine. So this is the high spin jump, okay? That's perfectly fine. But instead of the low spin staying low spin, it actually reverts back to high spin at the saddle points and then goes back down to low spin, okay? Now, of course, the migration enthalpy, therefore, is much smaller here for the low spin than the high spin. But it's not in its equilibrium position. It's actually only a few low spin ions around at this particular point, right? So this migration enthalpy depends really on where you are in the stability field, okay? So if you're at low pressure and you've mostly got high spin ion, actually, yeah, low spin ion does migrate faster, but there aren't any of them, okay? And actually, the same happens the other way around. If you now go to high pressure, well, okay, now you've actually got, what's going on here? I've lost my low spin and high spins. Okay, but the opposite thing happens now. Now the low spin ion, which is most of them, they actually diffuse slower than the high spin ions, okay, because they still keep going through this high spin state, okay? So the high spin state at the saddle point exists all the way through, probably all the way into super Earths and things. All right, and in fact, not only that, okay, not only do we have to worry about the ion changing spin during these calculations, it turns out as magnesium migrates, it also changes the spin state of the local ion sitting by as well, okay? And also it depends on which way it's going and so on. So there's a huge number of parameters you have to put into this. But the end result is we've got all this diffusion stuff, and now we'd like to do something with it, and so we'd look at things like the viscosity, okay? So in here we're just going to worry about diffusion creep for the moment, okay? Now it's not necessarily diffusion creep, but we're just going to model it as diffusion creep for the moment, and it depends on things like the grain size and the diffusion coefficient, okay? So up here is what we would calculate roughly for perovskite, okay? And down here is what we would calculate for ferropericles, okay? And in here is a little tiny change in the viscosity as a function of the spin collapse, okay? So it didn't really have much of an effect, basically because the one that is most iron rich, the one that has when it's a high spin, actually the low spin does go faster, but there are none of them. So it has a very small effect. But the interesting thing about this now, of course, is that actually the viscosity of our MgO or ferropericles is much lower than the viscosity of perovskite. Now, this is not new, okay, but we've calculated this all the way through the lower mantle now, and I think we've done this as best as you can do in terms of this sort of a mechanism for diffusion. And it's very clear that ferropericles is much, much weaker, okay? So, of course, if you're sort of a load-bearing perovskite, your viscosity should be up here. But, of course, if you ever connect your ferropericles in some way, right, and, of course, it's 20%, it's 20% by volume. So, in fact, there's a very good reason why you could easily connect it. Areas where you've got high strain, so, for instance, around subducting slabs or the edge of plumes, you should probably connect, or you could easily connect your ferropericles, and so your effective viscosity for the shear will be much, much lower than the bulk viscosity that you might imagine, okay? So I think, when we do all the modelling that we see and so on, we have to bear that in mind. I'm not the first person to say this by any means, but the fact is now that we've got these sort of numbers all the way through, I think it adds to the strength of that view. Post-perovskite, we've done the same thing in post-perovskite. The interesting thing about post-perovskite is it's incredibly anisotropic. I'm not going to worry too much about the anisotropicness or the anisotropy, but the interesting thing is that the diffusion of silicon, oxygen, and magnesium is much faster, certainly silicon and magnesium, along one of the directions in post-perovskite, and that opens up the idea that it's actually could be much weaker than perovskite, okay? Depends again on the mechanism. If it's diffusion creep, post-perovskite would actually probably be stronger than perovskite, and that's because you always have to take some diffusion in the slow direction, which is slower than in perovskite. But if it's in dislocation creep, and again, here's just some sort of deformation map. This is for olivine. We don't have a deformation map for the lower mantle yet for perovskite and post-perovskite. But again, so here's diffusion creep down here. We don't really know where we are, but in here is the sort of climb control mechanism, which it was alluded to and discussed and talked about, and that's controlled by diffusion. And so if you have some sort of power law creep with a climb-controlled mechanism, this very, very fast diffusion direction in post-perovskite could make it much, much weaker than in perovskite. And again, you were already told this by Patrick how that worked earlier, which is quite nice. In fact, there is also some experimental data on lysokalcium iridates, again, to show that the post-perovskite is much weaker, or could be much weaker than perovskite. And that agrees, again, with sort of various ideas. I don't know how much you believe all this these days, but this is quite a nice plot of the viscosity at the core mantle boundary. And white is high viscosity, and the sort of greyish colours are low viscosity. And these are hot spots. And the interesting thing about this plot is that actually the hot spots, the area where you might imagine it to be warmest, is actually the area that has the highest viscosity, which would be opposite if it was just a thermally controlled viscosity. And so one argument is just simply that these are areas where you've got perovskite because they're hot and they've never transformed to the post-perovskite, and these cooler areas, as Mike pointed out before, could be where you've got post-perovskite, and those are weaker, even though they're actually nominally cooler. We also argued, we're going to hear a little bit more about, maybe more about it tomorrow, I'm not so sure about that, but we've heard a bit about the post-perovskite to post-perovskite boundary and how wide it is and whether it happens in the lower mantle at all or whether it happens in the core. One of the ideas is actually it's rather wide, and so you would have a problem seeing it with reflectors, and we would argue that you can actually understand that in terms of shear-induced alignment, basically, of the post-perovskite, such that actually what you're reflecting off is not really the top of the post-perovskite to perovskite layer, but actually the development of LPO once the post-perovskite has been connected enough to take up all the shear via dislocation creep. Okay, so I just want to, this is sort of stuff that's sort of been done roughly. I just wanted to finish off with something slightly new. 5 minutes, good, since Mike gave this talk already for me. The other thing we've been doing is try to calculate the thermal conductivity. This is another of these great unknowns that people have put numbers on and so on. And we can calculate this in a simulation cell. Here's this simulation again of perovskite, just because it's pretty balls jiggling around. But what we can actually do is take out a bit of kinetic energy from here and then put it back in the other edge of the cell. And by doing that, we then make a sort of a thermal gradient through the cell. Okay. And given that we know the heat flow and we know the thermal gradient, we can then calculate the thermal conductivity from these sort of non-equilibrium simulations. Okay, so we take heat out here, or take kinetic energy out. We just slow the particles down a little bit, and then we speed them up over here. Okay, and by doing that, we can calculate the thermal conductivity. Here is our results. This is various different temperatures here. 300K, 475, can't read that number there, 4,000, 2,000. There are various experimental data here, almost all at 300 Kelvin, except for one here, it's about 475. We agree pretty well, not with all of it, but I think we agree best with the data that are best. Okay. The other thing to see, this is perovskite here, okay, this is the thermal conductivity, is that perovskite is does have a higher thermal conductivity at any particular temperature. Okay. And just like the anisotropy in the diffusion, it also is somewhat anisotropic in its thermal conductivity, although not very much. And here we've actually got two different models. We've done these simulations with a couple of different techniques, some using density functional theory, so this sort of ab initio, but also using pair potentials and so on, because these are very big, long calculations and very expensive to do. So here is basically one of these potentials. There are two potentials here, showing the average thermal conductivity of perovskite, and here is the average thermal conductivity of post-perovskite along some sort of geotherm, here and here. And in both cases, we get about an average of about 1.5 increase in the thermal conductivity, which isn't particularly a lot. One of these models actually predict that the A direction, one of the directions is much faster, so not much faster, but conducts heat a lot more efficiently than the other one. But there's a sort of the details of the anisotropy are not totally clear. The B and C here are slightly reversed in comparison with those two, but they're pretty similar anyway, so it doesn't really matter. So the question is, what can we do with that thermal conductivity? And this is what Mike gave the introduction to my talk for, so I wouldn't have to do this. Basically, we're using the same sort of flow models from Nathan Simmons, and we're using them to predict, with Andrew Walker, the anisotropy that you would get from such a flow model, again, by following a particle motion through D double prime, okay? And then we'll try to calculate the conductive heat flow and see if there are any implications. Again, this is some sort of a velocity map showing these here are the vertical velocities, and the arrows are horizontal velocities of this sort of a size. Okay. The interesting thing in this particular case, and I'm not arguing that for the veracity of this, I'll leave that up to the authors, I'm just saying this is what we're using, is that there's this quite strong upwelling here, presumably below the sort of Galapagos hotspot. You then, as we said, try to predict the anisotropy using elastic constants and the things we know about slip systems and so on from these models. Okay, and here's just showing roughly the anisotropy you get from various different models. It's not Mike's already talked about this. And then what we do is we put on our thermal conductivity and we say, okay, does any of this texture that developed, does it make any difference to the heat flow out of the core or horizontally or anything like that? Okay. So the first thing we've got is, this is the heat flow here, the total heat flow, the vertical heat flow out of the core, or the heat flux if you like. Okay, and if you've got all perovskite, so we just ignore the post-perovskite and all the texture and so on, you get something that looks like this. If you've got post-perovskite, you've got certainly some higher heat flows from the conductive part, and this is what you would expect because the conductivities are 50% higher. And again, this is if you've got a mixed phase, that is if it's where it's warm, it's perovskite, and where it's cold, it's post-perovskite, using some sort of phase diagram. Okay. In reality, it doesn't make a great deal of difference on these are just isotropic essentially models now. Okay, so we're not worrying about the anisotropy, we're just saying, okay, where's their perovskite, where's their post-perovskite. Doesn't make a great deal of difference, really. I mean, you either get 3.5, 4.9, or 4.8 for the heat flow. It's not clear to me that that makes much difference. You get a slightly different histogram of heat flow and various areas. So the perovskite has sort of this type of a histogram where it has most of the area has about this sort of a heat flow or heat flux, and whereas where you have a mixed phase, you have areas where higher heat flow and those with lower heat flow, depending on whether you've got perovskite or post-perovskite coming out of the core. So this could be potentially interesting. The other thing that we looked at was this sort of little Galapagos sort of area, again, which I pointed out before, which had these high vertical velocities, apparently. And then we've now calculated the heat flow, assuming it's totally with either an isotropic model or an anisotropic model. Okay, so the isotropic model looks a bit like this. Okay, so now what we have, these are horizontal heat fluxes in these sort of units, and the contours are the vertical heat flux. Okay, so that's the heat flux coming out of this area about 50 kilometers wide or deep at about 50 kilometers depth. If you put an anisotropic thermal conductivity into it, you then change the picture somewhat, and actually you sort of find that actually the heat flow apparently is actually going towards the plume rather than out of the plume. Okay, now this is sort of not exactly right. It's basically what it is saying that if you're flowing, if you have flow vectors that go like this, your anisotropic, you should normally conduct heat out from the center, okay? But if your conductivity is rotated round, or your structure, your post-perovskite is rotated round so that the fast heat conduction can actually sort of almost line up with the flow direction, okay? So you can get, so this sort of anisotropic thermal conductivity could potentially I suppose, help stabilize plumes, or at least it doesn't destabilize them as much as just a normal sort of conductivity. Whether or not that actually really matters, I think will depend on people doing some more detailed work on it. But I thought I don't want to bother with this one. So I thought I would just sort of throw that in as something different, partly because I get bored of the stuff that we have done and more interested in talking about things that we're doing now. But my conclusions are that, yes, we can use ab initio methods to calculate diffusion rates for minerals that are particularly because they're difficult to measure experimentally, and we can then use those to say something about their viscosity, depending on the mechanisms and so on. Ferropericlase is much weaker than perovskite throughout the mantle. I know that's been said before, but I'm just reinforcing that. Our results, spin transition slightly weakens it, but doesn't have much of an effect. So I think, one of the things that I've been banging on about for a little while now is that the lower mantle viscosity, at least in areas of high strain, can actually be controlled by ferropericlase rather than perovskite, and therefore is much weaker in certain places. Again, post-perovskite looks to us to be much weaker than perovskite, and interesting to see what comes out of that. And it also has a somewhat anisotropic conductivity, which may or may not help stabilize plumes depending on that amount of heat flow. Okay, thanks very much.